the mean value theorem, and related results. We begin by defining some terminology. If there's an open interval I containing C in which either f of C is less than or equal to f of x for all x in I, or f of C is greater than or equal to f of x for all x in I, then we say that f of C is a local extreme value of f. A local extreme value may be a local minimum value or a local maximum value. We can now state the following theorem. If f of C is a local extreme value, and if f is differentiable at x equals c, then f prime of c equals 0. Now, to see why this is true, suppose that f of c is a local maximum. That is, suppose that f of c is greater than or equal to f of x for all x near c, and that f prime of c exists. Then, for sufficiently small positive h, f of c will be greater than or equal to f of c plus h, and so the difference quotient f of c plus h minus f of c over h is less than or equal to 0. Now, this inequality remains true in the limit as h goes to 0 from the right. So f prime of c is less than or equal to 0. Also, for sufficiently small negative h, f of c is again greater than or equal to f of c plus h, and f of c plus h minus f of c over h is greater than or equal to 0 because h is negative. This inequality remains true in the limit as h approaches 0 from the left. So f prime of c is greater than or equal to 0. Since f prime of c is both greater than or equal to 0 and less than or equal to 0, it must equal 0. The extreme value theorem is a fundamental result concerning continuous functions on closed bounded intervals. Suppose that f is continuous on a closed bounded interval ab. Then there exist numbers c and d in ab such that f of c is less than or equal to f of x, which is less than or equal to f of d for all x in ab. Here, f of c is the minimum value of f on the entire interval, and f of d is the maximum value of f on the entire interval. Such values are often called absolute or global extreme values, as opposed to local extreme values. We must point out that either or both of these values may occur at the endpoints of the interval. For example, the minimum and maximum values of a linear function on a closed bounded interval are attained at the endpoints of the interval. This is true even if the function is constant. However, notice that if c is not an endpoint of the interval, then the value there is also a local minimum. In fact, it's the least of all of f's local minima on the interval. Similarly, if d is not an endpoint of the interval, then the value there is also a local maximum. In fact, the greatest of all of f's local maxima on the interval. Because of the preceding theorem, we can now extend the extreme value theorem as follows. If the number c is strictly between a and b, and if f prime of c exists, then f prime of c must be 0. And if d is strictly between a and b, and f prime of d exists, then f prime of d equals 0. Rolle's theorem. The essence of Rolle's theorem may be seen in this picture. If the graph of f is smooth, the slope of the tangent line must be 0 somewhere between any two numbers where the values of f are equal. Let's think about how this follows from our two preceding theorems. If the endpoint values of f on some closed interval are equal, then f must have an extreme value at some number strictly between the endpoints, provided that f is continuous on that interval. And if f is differentiable there, its derivative must be 0. That's essentially the proof of Rolle's theorem. Before we state the theorem, though, let's note that the slope might be 0 twice, or any number of times, between any numbers where the values of f are equal. With a constant function, it even happens everywhere. Now, here's the statement of Rolle's theorem. Suppose that f is continuous on the closed interval ab, and differentiable at all x in the open interval ab. If f of a equals f of b, then f prime of c is equal to 0 for some c in the open interval ab. The mean-value theorem is a generalization of Rolle's theorem, although we will use Rolle's theorem to prove it. One can think of the mean-value theorem as sort of a slanted version of Rolle's theorem. If the curve is smooth, then regardless of the endpoint values, there must be a point in between where the tangent line is parallel to the secant line through the endpoints of the curve. So here's what the mean-value theorem says. Suppose that f is continuous on the closed interval ab and differentiable at all x in the open interval ab. Then there is some number c in the open interval ab where f prime of c is equal to f of b minus f of a divided by b minus a. To prove this theorem, we'll apply Rolle's theorem to the function g of x equal to f of x minus f of b minus f of a divided by b minus a times x minus a. When x equals a, the second term here is 0, and the first is f of a. So g of a equals f of a. When x equals b, the second term is minus f of b minus f of a, or f of a minus f of b. And the first term is f of b. So g of b is also equal to f of a. And g is differentiable wherever f is, with g prime of x equal to f prime of x minus f of b minus f of a divided by b minus a. So there is a number c between a and b where g prime of c equals 0, and consequently f prime of c is equal to f of b minus f of a divided by b minus a. We note that if f fails to be differentiable at even one number in the interval, then the conclusion of the theorem may be false. For example, let f of x equal x to the 2/3 power. F prime of x is 2/3 times x to the minus 1/3, or 2 divided by 3 times the cube root of x, which does not exist at x equals 0. In fact, here's the graph of the function on the interval from -1 to 1. Notice that the line between the two endpoints of the graph is horizontal, and there is no place on that interval where the derivative is 0. Example. Show that the equation x cubed minus 3x squared plus 6x equals 5 has exactly one real solution. Let's define f of x to be x cubed minus 3x squared plus 6x minus 5, so that the roots of f correspond to the solutions of our equation. Now, f is continuous and differentiable everywhere because it's a polynomial. And since f of 0 is equal to -5 and f of 2 is equal to +3, the intermediate value theorem tells us that f has a root somewhere between 0 and 2. So this tells us that our equation has at least one real solution. Now we need to show that there can't be two solutions. Now Rolle's theorem tells us that between any two roots of f, there must be a root of f prime. So let's have a look at f prime. It's 3x squared minus 6x plus 6, or 3 times x squared minus 2x plus 2. Then by the quadratic formula, if f prime of x equals 0, then x must be one of the numbers 2 plus or minus the square root of 4 minus 8 divided by 2. But those are the complex numbers 1 plus and minus I. So we conclude that there is no real number x for which f prime of x is equal to 0. Because of Rolle's theorem, if f had two roots, f prime would have to be 0 somewhere. So therefore f cannot have two roots. And so the equation cannot have two solutions. Example. Let f be continuous on the closed interval ab and differentiable on the open interval ab, with f prime of x between two numbers little m and big M for all x in the open interval ab. Show that f of x minus f of t is always between little m times x minus t and big M times x minus t when t is less than or equal to x and t and x are in the closed interval ab. Now let's notice that this is trivially true if t is equal to x, since all three parts of the inequality are 0. So let's assume that t is less than x. Then the mean value theorem tells us that for some c between t and x, f prime of c is equal to f of x minus f of t divided by x minus t. So by assumption, this quantity is between little m and big M. So we'll multiply through by x minus t and conclude that f of x minus f of t is between little m times x minus t and big M times x minus t. We can interpret this result graphically by thinking of t as fixed and drawing lines with slope little m and big M through the point t f of t. The result says that the graph of f must lie between those two lines. Increasing and decreasing values on an interval. Let f be a function whose domain includes an interval I, and let t and x denote arbitrary numbers in I. Then we say that f is increasing on I if f of t is less than f of x whenever t is less than x, and that f is decreasing on I if f of t is greater than f of x whenever t is less than x. Notice that an increasing function preserves inequality, while a decreasing function reverses inequalities. Now consider the function whose graph is shown here. There's an interval whose right endpoint is the number p, on which f is increasing. Notice that on that interval, t less than x implies that f of t is less than f of x. Also, f is decreasing on the closed interval from p to q. On that interval, t less than x implies that f of t is greater than f of x. And on an interval with left endpoint q, f is again increasing. Let's introduce a little bit more terminology. Let I be an interval. The open interval obtained by excluding endpoints from I is called the interior of I. So the interior of the closed interval 0, 1 is the open interval 0, 1. The interior of the closed interval 0 to infinity is the open interval 0 to infinity, and so on. Also, the interior of any open interval is itself. This terminology allows us to state the following theorem a little more concisely. Let I be an interval, and suppose that f is continuous on I and differentiable on its interior. Then, if f prime of x is positive for all x in the interior of I, then f is increasing on I. If f prime of x is negative for all x in the interior of I, then f is decreasing on I. F prime of x equals 0 for all x in the interior of I if and only if f is constant on I. Let's look at a proof of this result. Let t and x be in I with t less than x. Then the mean value theorem tells us that there is a number c in the open interval tx where f prime of c is equal to f of x minus f of t divided by x minus t. Now, if f prime of x is positive for all x in the interior of I, we know that f prime of c will be positive, which implies that f of x minus f of t is positive, since x minus t would also be positive. And we conclude that f is increasing on I. If f prime of x is negative for all x in the interior of I, we know that f prime of c is negative, which implies that f of x minus f of t is negative, since again x minus t is positive, and we conclude that f is decreasing on I. Finally, if f prime of x is equal to 0 for all x in the interior of I, then f prime of c is equal to 0, which implies that f of x minus f of t is equal to 0, and since x and t are arbitrary, we conclude that f is constant on I. The one remaining piece of the theorem to be proved is something we already know, and that is that the derivative of a constant function is equal to 0. Example. Let f of x equal 3x to the fourth minus 4x cubed minus 12x squared plus 10. Find the intervals on which f is increasing and the intervals on which f is decreasing. We first compute the derivative f prime of x and simplify and factor if possible. We'll use the power rule here and find that f prime of x is equal to 12x cubed minus 12x squared minus 24x. We notice that 12 is a common factor as well as x to the first power. So we have 12x times x squared minus x minus 2, and that quadratic factors into x plus 1 times x minus 2. So now we observe that f prime of x is equal to 0 at x equals 0, negative 1, and 2. And now to determine where f prime of x is positive and where it's negative, we'll use a graphical device. We'll plot a copy of the real number line showing the zeros of f prime, and we'll plot the sign of f prime along that axis. Let's start with large positive values of x. If x is greater than 2, it's easy to see that all three factors of f prime are positive. And so f prime of x will be positive. Now let's look at large negative x. If x is less than minus 1, then it's easy to see that all three factors of f prime are negative, and so on the interval from minus infinity up to minus 1, f prime of x is negative. Now, between 0 and 2, we can use a test point of x equals 1 and conclude that f prime of x is negative between 0 and 2, and then we'll note that between minus 1 and 0, x is negative, x plus 1 is positive, and x minus 2 is negative, and so we have two negatives and a positive to give us an overall positive value. Notice that there's a sign change at each of the zeros of f prime of x. This is guaranteed to happen when the corresponding factors of f prime are all raised to odd powers. Here, each of the factors is raised to the first power. So f prime of x is negative between minus infinity and minus 1, as well as between 0 and 2. So we'll conclude that f is decreasing on the closed interval from minus infinity to minus 1 and the closed interval from 0 to 2. Also, f prime is positive on the open interval from minus 1 to 0, as well as the open interval from 2 to infinity. So we conclude that f is increasing on the closed interval from minus 1 to 0, as well as the closed interval 2 to infinity. Here's the graph of that function. Notice that where f is decreasing, we have a negative slope, and where f is increasing, we have a positive slope. In fact, the information that we have gained concerning where f is increasing and where it's decreasing can go a long way toward a hand-drawn sketch of the graph. Another example. Let f of x equal x to the 1/3 power times 2 minus x. Find the intervals on which f is increasing and the intervals on which f is decreasing. First, we compute f prime of x and simplify. For this purpose, it's a good idea to expand the product and write f of x as 2 times x to the 1/3 minus x to the 4/3. That way we can avoid using the product rule to take the derivative. So now using the power rule, we have f prime of x equals 2/3 x to the minus 2/3 power minus 4/3 times x to the 1/3 power. Now let's write the first term as 2 over 3 times x to the 2/3 power, and then multiply the second term by x to the 2/3 divided by x to the 2/3 to obtain the common denominator. Now let's combine the two terms, and we have 2 times 1 minus 2x divided by 3x to the 2/3 power. Now that form makes it easy to see that f prime of x is equal to 0 at x equal to 1/2, and it's also undefined at x equals 0. So these are the two numbers where it's possible for f prime of x to undergo a change in sign. Now let's plot the sign of f prime of x over a copy of the real number line. First, we notice that if x is large and positive, the numerator of the fraction is negative, the denominator of the fraction is positive, and so f prime of x is negative. If x is negative, it's easy to see that the numerator and denominator are both positive, and when x is between 0 and 1/2, we also have a positive numerator and a positive denominator. So we have the interval from 1/2 to infinity where f prime of x is negative, and so f is decreasing on the closed interval from 1/2 to infinity. We also know that f prime of x is positive on the interval from minus infinity to 0, as well as the interval from 0 to 1/2, and so f is increasing on the closed interval from minus infinity to 0 and on the closed interval 0 to 1/2. Now we can combine those two into one statement and simply say that f is increasing on the closed interval from minus infinity to 1/2. Now let's have a look at the graph of this function. Notice that we have a vertical tangent line at 0, but on both sides of 0, the tangent line has positive slope, at least up to 1/2, where the tangent line is horizontal, and to the right of 1/2, the tangent line has a negative slope. Question. We know that under the proper conditions, if f prime of x is positive on an interval I, then f is increasing on I, but is the converse of that true? In other words, if f is increasing on I, can we conclude that f prime of x must be positive for all x in the interior of I? Well, the answer to that is no, and the simple example f of x equals x cubed demonstrates that. We know that that function is increasing for all x, that is on the interval from minus infinity to infinity, but f prime of x, which is 3x squared, equals 0 when x is 0. So we only can say that f prime of x is greater than or equal to 0 on the interval minus infinity to infinity. Now what we can say is the following. Let I be an interval and suppose that f is continuous on I and differentiable on its interior. These are our usual assumptions. Then, if f is increasing on I, then f prime of x is greater than or equal to 0 for all x in the interior of I. And if f is decreasing on I, then f prime of x is less than or equal to 0 for all x in the interior of I. To prove this, we can simply use the definition of the derivative as well as the property of limits. Suppose that f is increasing on I, and let x be in the interior of I. Then, the difference quotient f of x plus h minus f of x divided by h will be positive for all h small enough that x plus h is also in the interior of I. This is because if h is positive, f of x plus h is greater than f of x, and if h is negative, then f of x plus h is less than f of x. And so the quotient turns out to be positive in both cases. So the derivative at x is the limit as h goes to 0 of a positive quantity, which implies that the limit f prime of x is greater than or equal to 0. The case where f is decreasing is similar. Example. Let f of x equal 6x to the 5th minus 15x to the 4th plus 10x cubed. Find the intervals on which f is increasing and the intervals on which f is decreasing. So let's look at the derivative. F prime of x is 30x to the 4th minus 60x cubed plus 30x squared. Now we can factor a 30 and an x squared and obtain 30x squared times x squared minus 2x plus 1. We further factor this to obtain 30x squared times x minus 1 squared. So we conclude that f prime of x is equal to 0 at x equals 0 and at x equals 1, and f prime of x is positive elsewhere, because both of the factors there are squared. So f is increasing on the interval from minus infinity to 0. It's also increasing on the closed interval 0 to 1, and the closed interval 1 to infinity. Together, these intervals comprise the entire real number line, so f is increasing on the interval from minus infinity to infinity. Let's have a look at the graph of the function here. Notice that we simply have two flat spots, one at x equals 0 and the other at x equals 1, and otherwise the graph has a positive slope. Now this example illustrates the following result. Let I be an interval, and suppose that f is continuous on I and differentiable on its interior. Then, if f prime of x is greater than or equal to 0 for all x in the interior of I, and if f prime of x is equal to 0 at only finitely many x in the interval I, then f is increasing on I. And likewise, if f prime of x is less than or equal to 0 for all x in the interior of I, and if f prime of x equals 0 at only finitely many x in I, then f is decreasing on I.